Okay. Can you hear me on the back?
Okay.
Good.
The sound is tested. Alexander, the floor is yours.
Okay, thank you so much. Thank you everybody for being here. Thank you to the organizers for planning and executing such a wonderful conference. I'm having a great time so far. And I'm very happy to be telling you about these two relatively recent works in collaboration with Michal Heller, Michal Spalinski, and Ben Withers, who is right there in the audience. So the topic of this talk is relativistic hydrodynamics, as well as the quantum field theories that have a dynamical regime were described by this effective field theory. Now, Blaise already did an amazing job in explaining to you what hydrodynamics is, why and how it emerges. So thanks to him, I can afford to be brief in reviewing it. So I just want you to remember that when the number of local degrees of freedom of the underlying quantum field theory in consideration is sufficiently large, relativistic and stochastic fluctuations are negligible. Relativistic hydrodynamics is a classical effective field theory formulated in a gradient expansion. And this gradient expansion is going to contain infinitely many terms, gradient according to the number of space-time derivatives they involve. Each term is going to have a functional form fixed by the field content and the underlying symmetries of the system, and it's going to be weighted by a transport coefficient, which can, of course, not be determined at the level of the effective field theory itself, and has to be either measured experimentally or computed theoretically. So relativistic hydrodynamics, a theory of relativistic hydrodynamics, is defined for us by an infinite sequence of transport coefficients. And the main question I want to address in this talk is whether an arbitrary sequence of transport coefficients defines a valid theory of relativistic hydrodynamics or not. And as you can probably guess, otherwise I wouldn't be telling you about this, the answer to this question is negative. And the main message I want to convey in this talk, the main point I want you to remember, is that relativistic causality is going to imply that every single consistent theory of relativistic hydrodynamics, as I have defined them, is going to be contained inside a universal convex geometry in the infinite dimensional space spanned by the transport coefficients. And I will refer to this universal convex geometry as the hydrohedron. And please keep in mind that when I here say consistent theory of relativistic hydrodynamics, I'm including every quantum field theory with a hydrodynamic regime of the form I explained. Okay? So this was the talk in 3 slides. Now let me start with the actual talk. So I will introduce the hydrohedron in the final part of the talk. The hydrohedron is going to emerge, spoiler alert, from a new infinite set of relational two-sided bounds on all the transport coefficients that I will construct. Since transport coefficients are dimensionful quantities, it is essential to measure them against another dimension, another energy scale in order to form these bounds. So the second part of the talk is going to be devoted to what this energy scale is. And before that, what I'm going to do now is to take you the basic ingredients that enter into sections 2 and 3, into how the hydrohedron is constructed. So just starting with the basics, imagine that we take some equilibrium state and we act upon it by an external perturbation of characteristic amplitude A and characteristic frequency omega and characteristic wave vector k, all measured in units of the temperature. So if this perturbation is arbitrary, we are going to end up in a fully out of equilibrium regime, which in IDS-CFT is described with the techniques of numerical GR. Now, hydrodynamics, as a valid effective field theory description, sits here when the frequency and the wave vector are sufficiently small. In holography, this is the regime where fluid gravity duality applies. Now, there is a complementary regime when the description of the out of equilibrium dynamics of this quantum field theory is going to simplify, and that was also mentioned in Blaise's talk, is the linear response theory regime, when the amplitude of this external perturbation is sufficiently small, but its frequency, its characteristic frequency, and spatial momentum are still arbitrary. Okay? So in holography, this is nothing but the regime described by linearized perturbations of black brains. So in the talk, the most important regime for us is this region here, where hydrodynamics and linear response theory are going to overlap in validity. Okay? So we're going to be looking at the small amplitude limit of relativistic hydrodynamics, or the small frequency, small momentum, and small spatial momentum limit of linear response theory. Now,
can I ask you haven't mentioned it, but the
yeah.
diagram suggests that's true for holographic theories. Is your
no, well,
that's only for holographic or more general?
I have holographic theories in mind when I wrote this diagram. Yes.
There is also more general.
the results, the results rely on some assumptions, so as long as assumptions hold, the results are going to hold. So assumptions are microcausality and analyticity assumption I will explain. I think the analyticity assumption restricts you to large chain quantum field theories and no more than that. But I will explain this. The diagram is just, since this is Eurostrings, I thought it would be nice to relate the diagram to ADS CFT. And by the way, I took the diagram from a review by Rangamani and Juveni from 2011, so the diagram is not my idea. Okay, so just to give you some basics of linear response theory, the basic object we are going to be focusing on is the retarded thermal two-point function, defined in this way in quantum field theory. And since the thermal equilibrium state is going to be translational invariant and rotational invariant, we are going to be mostly working with the momentum space counterpart of this quantity, which I will denote position and momentum space with the arguments of the function. Now, the basic notion for us was already introduced by Blaise, and it's the notion of a mode. So a mode for us is going to be a singularity of the momentum space retarded thermal two-point function, and it's going to be characterized by a dispersion relation, omega of k, telling you where the singularity is located in the complex omega plane as the external spatial momentum, as the spatial momentum is varied. Okay? Now, the usefulness of the mode notion was also explained clearly in Blaise's talk, and it's that they organize the response of the system to the external perturbation in a clear and hierarchical manner. And just as a reminder, in holography, a mode is going to be a single pole of the momentum space retarded thermal two-point function, which corresponds directly to a quasi-normal mode of a bulk black brane. Okay? So for the purposes of this talk, there's two fundamentally different kinds of modes we need to consider. So the first kind of modes are modes such that their frequency vanishes as the wave vector does. These modes represent long-lived and slowly varying excitations of the thermal state and are called hydrodynamic modes because they are the modes captured by relativistic hydrodynamics as an effective field theory. Now, any mode that doesn't obey this property is unsurprisingly called a hydrodynamic mode and has the feature that its frequency is finite at zero momentum. Now, in a dissipative system, this quantity typically has a negative imaginary part, so these non-hydrodynamic modes are typically transient decaying excitations. Okay? So, since modes are quasi-normal modes, if you compute them in holography, they would form the standard Christmas tree structure for real wave vector. Okay? So, the crucial fact for us, remember, we are working in this overlapping domain of validity between relativistic hydrodynamics and linear response, is that relativistic hydrodynamics, as an effective field theory formulated in a gradient expansion, will predict for us what is the small wave vector expansion of the dispersion relation of the hydrodynamic modes. This is an infinite series. It has some expansion coefficients, Cn. These are straightforwardly related to the transport coefficients that appear in the position space gradient expansion. And from now on, I will trade one set of transport coefficients for the other, and I will take these numbers here as my transport coefficients. Okay? Just to have some example in mind, if you take the hydrodynamic sound mode of a neutral relativistic fluid, the low order coefficients correspond to the speed of sound and the sound attenuation length. If you take a shear mode, you get a diffusivity. Okay? And these series continue up to arbitrarily high order. Now, what comes next is probably the most important slide of the talk. So, what I want to mention now and emphasize is that relativistic causality is going to impose a positivity constraint of on the dispersion relation of any mode in any quantum field theory. Now, causality is the statement that if I act on the system with a perturbation localized at x equals 0, the response has to be supported only in the future light cone of x equals 0, right? So the retarded thermal two-point function is going to vanish outside the future light cone. And if now I assume that this retarded thermal two-point function is a temporal distribution, it then follows that this momentum space counterpart is analytic in the open future light cone of the imaginary part of the form momentum p, which in terms of omega and k takes this form. Okay? So this object has to be analytic in this region, implying that any mode, which remember is any singularity of this subject, has to be strictly located outside of it. And hence, any mode in any theory which respects relativistic causality has to obey this fundamental inequality. You can see it here. The imaginary part of the mode frequency at a given k has to be smaller or equal than the norm of the imaginary part of the wave vector k. Okay? So this is the basic building block upon which everything else I'm going to tell you in this talk rests upon. Okay? Now, as I told to Costas before, there is another assumption we will make, and this assumption is that the dispersion relations in the underlying microscopic quantum field theory are also analytic at k equals 0. meaning that they can be exactly captured by the prediction of relativistic hydrodynamics as I have defined this effective field theory. Now, physically, so meaning that they basically have this form. Okay. Now, physically, the absence of non-analytic terms in this expression is directly correlated with the with the fact that stochastic fluctuations are negligible, and this assumption is going to restrict us to large N QFTs, but in particular, every holographic QFT in the large N, large lambda limit is going to respect it. Okay? So this is the kind of microscopic theories that we are going to be able to constrain. Okay, so in the rest of the talk, what I'm going to do is to explore the consequences of the causality condition I introduced and this analyticity assumption. First, I want to mention a sanity check. If you assume that the dispersion relation is analytic at k equals 0, and you explore the implications of the causality condition, you automatically find that the speed of sound squared is upper bounded by the speed of light squared, which is 1 in my units, and that the diffusivities are always non-negative. But these two elementary consistency checks are just the tip of the iceberg, because it turns out that relativistic causality and analyticity impose powerful constraints on relativistic transport at all orders. And these constraints, as I think I already mentioned, but I will remind you, will take the form of a novel infinite set of relational two-sided bounds on all the transport coefficients. And these two-sided bounds are going to be optimal when expressed in units of capital R, which is the convergence radius of the small momentum expansion that I introduced before. Okay? Okay, so since I already mentioned the topic of bounds on transport twice, I want to have a word on them. Of course, the possible existence of universal bounds on transport is not a new topic, and the most celebrated example that you may have in mind is the KSSS conjecture. Now, the methods I'm going to deploy in this talk cannot prove such lower Planckian bounds on the diffusivities, meaning simply that, as you would probably have expected, these lower Planckian bounds on diffusivities do not follow from relativistic causality. What I'm going to do is to give you a sharp counterpart of a previous qualitative upper bound on the diffusivity obtained from causality considerations by Harman, Harnold, and Mahajan in 2017. And I'm not only going to give you a sharp counterpart of this bound on the diffusivity, but I'm going to generalize it to all transport coefficients. Okay? So this is what we are going to do. So now I told you that the optimal energy scale to measure the transport coefficients again is this capital R, the convergence radius of this small momentum expansion, so I want to devote some time to it. Okay, so first, obvious point. So R can be either measured or computed explicitly if the underlying microscopic quantum theory in consideration is known. And starting from the work by Ben in 2018, this quantity has been under intense scrutiny in holography. And this study was performed on a case-by-case basis, and in every example known to date, this scale is finite and is set by a branch point singularity of the dispersion relation. Okay, at this level, are empirical facts, established along a sufficiently high number of examples to be believable. Now, these empirical properties, as we showed in our first paper in the subject, follow straightforwardly from the causality condition and analyticity. So in this paper, among others, we proved two theorems that I'm going to use now. The first theorem is that if I have 5 minutes? Okay. So I will try to be fast. So the first theorem is that if the dispersion relation is an entire function of k, it has to be at most a polynomial of degree 1 in k. Now, since transport coefficients associated to dissipative effects enter at order k squared or higher, this implies that R is finite in any dissipative relativistic theory of transport, and by elementary complex analysis, R is set by the singularity of the dispersion relation, which is closest to the origin in the complex k plane. But this theorem doesn't tell you what this singularity is. But you can also show that if this function has a pole of any finite order, it's going to violate the causality condition sufficiently close to it. So R is set by a branch point singularity. Now, from these two facts, and now I'm going to start skipping slides because I only have 5 minutes and I want to get to the hydrohedron, okay? So, From this observation that relativistic hydrodynamics, let's say the energy momentum tensor, these two theorems actually allow you to prove that non-hydrodynamic modes are inevitable in any consistent dissipative theory of relativistic transport. So the argument schematically builds upon three facts. The first fact is that the relativistic hydrodynamics predicts a single mode in the shear channel. Our analysis predicts that this mode has a branch point. And rotational invariance tells you that both shear and sound modes are going to become degenerate at k equals 0. So if you combine these three facts, you infer that there is a non-hydrodynamic mode in the shear channel and in the sound channel. Meaning that R is going to mark for you the momentum scale at which non-hydrodynamic degrees of freedom are going to stop being negligible, they would become relevant, and cannot be neglected anymore. So it is natural to interpret R as the natural UV cutoff of relativistic hydrodynamics in the linear response regime. And this general interpretation of R actually matches all the previous explicit computations of this quantity in holography, but I'm not going to discuss that into that. So in my last 5 minutes, I will tell you about the two-sided bounds and the hydrohedron itself. So the strategy to obtain this infinite set of two-sided bounds on the transport coefficients is to take the causality condition and transform it into a moment problem. So for those of you that know about this mathematical subject, we're going to take the causality condition and transform it into a truncated trigonometric moment problem, which I am explaining here, but I will skip these slides because they are not that important. This is explained in the paper, so you can go and read it. And I have to mention that this strategy, we learned this strategy from the S-matrix booster program. So in the end, what we have to do is to take the causality condition, but I will be brief. And we take the causality condition, we construct a unit normalized measure, we focus on the moments of such measure, and from the positive semi-definiteness of this measure, we get to the conclusion that this moment matrix, which is an infinite number of them, has also to be positive semi-definite. Now, the moments, the measure follows from causality condition. Moments of the measure is straightforwardly related to transport coefficients. So, imposing that each matrix for n equals 1, 2, 3, 4, etc., is positive semi-definite, gives you an infinite number of bounds on the transport coefficients. So this is how the bounds are obtained, okay? And this infinite set of bounds is going to lead to this universal convex geometry in the infinite dimensional space of transport coefficients. We are referring to as the hydrohedron. By construction, every theory which is not inside the hydrohedron or at its boundary is incompatible with relativistic causality and hence excluded from first principles. And I want to emphasize that to make manifest this universal structure, it is essential to measure the transport coefficients in units of R. R is going to absorb for you dependence on space-time dimension, coupling strength, temperature and other thermodynamical potentials, which makes, in my opinion, this observation makes, in my opinion, learning new general lessons about R an extremely valuable endeavor, okay? So now I will present to you the hydrohedron at last. So if we take a diffusive mode with this dispersion relation, every coefficient is purely imaginary. We take these beta n's as our transport coefficients. Beta 2 is minus the diffusivity. We run this machinery, this moment problem machinery, and we arrive at an hierarchical set of bounds. This structure would continue forever. So at leading order, what we find is an upper bound on the diffusivity, which provides the sharp, rigorous counterpart of this qualitative bound I mentioned before. Next order, we find a two-sided bound on beta 4, in which the upper bound depends non-trivially in beta 2. Next order, beta 6 is bounded from above and from below. Its bound depends non-trivially in the transport coefficients of previous orders, and so on. So if you take the three-dimensional projection of the infinite-dimensional hydrohedron, it is this beautiful convex shape you can find here, and taking two-dimensional projections in turn, you get these regions. You see that most of the transport coefficient space has been excluded by the two-sided bounds. And in these plots, you see 2 points. The red cross is n equals 4 Susi Miss in the holographic limit, and you see that it lies well within the boundaries of hydrohedron. The open circle, it's a conformal kinetic theory in the relaxation time approximation, also contained within. It's here as a weakly coupled representative. For the sound channel, you can play exactly the same game. You get again an infinite set of hierarchical two-sided bounds, one order, upper bounded, lower bounded by some bounds which depend non-trivially on the transport coefficients on all the previous orders. And this is the Matryoshka structure, it stands forever. This is the corresponding plot in the sound channel. And for the sake of time, I'm just going to tell you very briefly something about the hydrohedron boundaries. So it turns out that the boundaries of the hydrohedron set by the moment problem are open. this we showed explicitly by a full computation. So there is no special theory living at those boundaries, but other boundaries, which are set by these conditions, which may emerge from a local analysis around k equals 0, are not necessarily open. And there is a rather trivial physical theory living there, which is that of a fluid in which the speed of sound equals to the speed of light. Just as a curiosity, if you have a fluid in which the speed of sound equals to the speed of light, the causality condition is going to imply that all the dissipative transport coefficients vanishes and the dispersion relation is exactly this. Okay? So there are some open questions that I think this work motivates. The first set of questions pertains to R. I think it would be interesting to understand this quantity in a deeper level and relate it to some other easily computable quantities, such as the temperature or the non-hydrodynamic gap. And regarding the hydro-hydro, much work remains to be done to see if this analysis can be generalized. We would need to consider the generalization to nonlinear transport, and it would be fascinating to see if we can systematically incorporate stochastic effects. So with this, many thanks for your time. Sorry if I went a little bit over it. Yeah, thanks. Perfect. Good, good. I put some effort into it. Yeah.
Any questions for Alexandre? Mark.
Okay, I'm going to do the water bottle trick, if you allow me.
So can you elaborate on this large N assumption? I thought that stochastic effects can be suppressed also by going to large temperatures so that you have large local entropy density.
Yeah, I assume temperature was order 1 and that I sending entropy density to infinity by sending n to infinity, but I absolutely agree with what you said. Yeah. Yeah, in the end, if you compute a loop correction due to thermal fluctuations to some observable, it's suppressed by 1 over S. So yeah, you're absolutely right. Yes.
Do I understand correctly that you've used all orders in gradient expansion for this? So is there anything you can say about truncated hydrodynamics with this machinery?
If you take the dissipative, if you take the dispersion relation and you truncate it at a finite order, what you get is a polynomial of order greater than 1. It's going to inevitably violate the causality condition. So such a theory with such a mode cannot be compatible with relativistic causality. That's the statement. Which this connects nicely to the issue of the initial value problem in relativistic hydrodynamics formulated in a gradient expansion, and how, this intermingles with truncating the expansion. So, it's a highly non-immediate question to answer. But we can discuss. I mean, it's a topic I really love, so yeah, I'm very happy to discuss it.
So, in your bounds, what happens when the radius of convergence becomes infinite?
All the dissipative transport coefficients have to be 0. Because, for instance, look at the diffusivity here. Let me say, if you send R to infinity, if you say R to infinity, this is negative, so yeah, it's beta 2 has to go to 0.
So say that R is fixed by temperature.
Yeah.
Then we're thinking about the very, very high temperature limit. Why is there no...
Sorry, I'm not...
Why can you have sound but not diffusion, for instance?
Sorry?
Why can you have sound but not diffusion?
No, for sound it's the same. I mean, you can have a propagating sound mode, but it wouldn't be attenuated, I guess.
So this is essentially saying you're going to the non-interacting limit of
yes.
the theory.
Yes, I would say so, yeah. Yes, exactly. Yeah, I think it's fair to say that.
Kostas had a question.
Can you elaborate a little bit on the assumption that especially retarded correlators and analytic is 0?
No, yeah. So I'm just saying that the dispersion relation, so you take a singularity of the retarded two-point function in momentum space, and you see how it depends on the wave vector. This frequency depends on the wave vector. And the assumption is that this is an analytic function of k at the origin. That's it.
Are the counterexamples? Are they? Huh?
Omega of k.
Yeah, omega of k is analytic at k equals 0.
Omega of k.
Omega of k.
Yeah, omega of k. But sorry, this is this is semantics. When we say dispersion relation, we always mean omega of k. I know everybody. Yeah, exactly. So yeah, thanks, man. So the assumption is clear now, right? Perfect.
I would like to ask one question. So
Sure.
relativistic hydrodynamics, when you go to in the gradient expansion,
Yes.
has a well-known problem at second order because sort of naively you violate causality.
Yes.
Right. So this should address that. So how does it address the Israel-Stewart
Well, but it's
relativistic
different.
hydrodynamics?
You mean, but when you say relativistic hydrodynamics, you're talking about this gradient expansion, or you're talking about MIS?
What?
So when you say relativistic hydrodynamics, what do you mean?
Yes. Just relativistic hydrodynamics.
Yes. So if you truncate, so you have a gradient expansion. This is a perturbative expansion in gradients.
Yes.
If you truncate it,
Yes.
right, and you treat it as exact, it's not going to respect relativistic causality.
Okay.
It would give you a mode which is, let's say, a polynomial in K with order higher than 1. That's automatically violating it. So now, truncating and using it at finite gradients at operations that don't commute. Right? And this is something that everybody should keep in mind, in my opinion.
Okay. Thank you so much.
Okay. Thanks, guys.
Okay. We reconvene at 2 o'clock, right?